Hello students. You know what is geometric series. In the previous video, I've explained to you what is geometric series. Now there are a few more other types of series that we're going to look at. Okay, there are telescoping series, harmonic series, power series, Taylor series, and so on. So today we're going to look at a series called telescoping series. Okay, now the same thing we will do on what we did for the geometric series. We want to determine the sum of the series, and then we want to determine the convergent and divergent for this series. Okay, let's look at the definition for this series. Okay, so why this is called telescoping. So let's say you're given a series in this form, okay, and I equals to 1 to n ai plus 1 minus ai. Okay, so for geometric series, you know a series in the power of 1 minus uh, n or n minus 1. Okay, so it's a power of something, you know, it could be a geometric series. But for telescoping series, you have a summation where successive term will cancel out. Okay, let's look at this one. When let's say when I is 1, I have a2 minus a1. Okay, and then what I do, this is a series, right? So I add them, and then I equals to 2 a3 minus a2, and then I equals to 3 a4 minus a3. Okay, so let me just write, this is when I equals to 1, I equals to 2, I equals to 3. Now what about when I is n? Okay, when I is n. So what we can find here, we can see that now when I equals to n, what we have here, I'm just trying to find my blue color. Oops, sorry. Okay, so when I equals to n, what we have here, so we have an minus 1. Okay, this is when I equals to n. No, before this is a term before that. Sorry, so this is when before n minus 1. This is the term when I equals to n minus 1. Now when I equals to n, now I equals to n, so we have plus, okay, so I have I don't know what's happening with my marker here. So I have plus n plus 1, an plus 1 minus an. Okay, so this is what you get. Now let's cancel out the term here. You can see that this a2 and a2 cancels out, a3 and a3 cancels out. So what happened here? a4 will also cancel out with whatever term next when I equals to 4. So all this term will also cancel out, except this term will also cancel out with this one, except for this term and this term, right? So that will leave you with an plus 1 minus a1. Now this is called the telescoping series. Okay, this type of series can be easily calculated since a few terms will be cancelled out. That will leave you to only some term. Okay, let's look at one example here. Okay, so this is the example. So show that the series summation n equals to 1 to infinity, 1 over n plus 1 is convergent. Okay, is convergent. And find its sum. Okay, so remember, to find the sum, we need to get the partial sum. Okay, let's look at this example here, how to solve this series. So, of course, this is not a geometric series, right? There's no term involving power. So, what we need to do here, we need to find the partial sum. Because we want to find the sum, we need to find the partial sum. So, to find the partial sum, meaning something like this, Sn equals to summation I equals to 1 to n, 1 over I minus 1, where it means that this will be what I can do here. Well, let's look at when I equals to 1. I have 1 and then 1 minus 1, 1. That is 2. I will have 3. So this is 1. 1 minus 1 is 0. Oh no, sorry. What am I doing? This is not minus, this is plus. Okay, so and then I have 1 over 2, 2 plus 1 plus 1 over 3, 3 plus 1 plus 1 over 4, 4 plus 1. Okay, so just look at the term here. I have 1, I have 2, 2, 3, 3, 4, 4, 5. So the n term should be n plus 1. Okay, so this is my this is the partial sum that I can write there. Now I need to simplify the partial sum. So simplifying the partial the partial sum, simplifying the sum using partial fraction. Okay, I'm sure you have learned this partial fraction before. So we want to simplify this. Okay, so what we get here, so 1 over I plus 1 equals to, this is a partial fraction. Okay, how do we do this? Let me just write it down. So what's the partial fraction here? Is minus 1 over I plus 1. Is it correct? Is this correct? Let me just a quick check. So simplifying the denominator, I plus 1 minus I, that will give me I plus 1. I minus I cancels out. That will give me 1 over I plus 1. Okay? Which is similar with the given term on the right hand side. Okay, so now this is a partial fraction. So what I can say, the summation Sn, the partial sum, I equals to 1 to n, 1 over I plus 1 equals to summation I equals to 1 to n, 1 over I minus 1 over I plus 1. Now you can ask me, how did I get it here? So you need to find the partial fraction. Let me just put a note. Okay, you need to write the partial fraction for this term here, I plus 1. Okay, and this is what you get when you write the partial fraction. Now, once you got the partial fraction, what you do here, it'll be easier to simplify. But before we do that, let's substitute when I equals to 1 and so on. So when I equals to 1, I have 1 minus 1 over 2. Plus when I equals to 2, 1 over 2 minus 1 over 3. When I equals to 3, 1 over 3 minus 1 over 4. So you can see the pattern, right? So when I equals to n, 1 over n minus 1 over n plus 1. So this is a telescoping series because I can cancel out this term, this term, this term. So that will leave me with the term involving 1 minus 1 over n plus 1. Okay, I've shown you earlier on. So every term will cancel out except the first and the last term. Okay, so this is what you call telescoping series. Now, you can find to find the value of this series here. So take the limit of n approach infinity Sn, which is limit n approach infinity 1 over n plus 1. Okay, when n approach infinity, 1 over infinity is 0, so that will give you 1. Okay, so therefore we can say the series convergent because there's a value here, and we can say that this is what we say, the series given series 1 over n plus 1 is equals to 1. Okay, so you can there is also a term for this series where we can say that whether the series, we call it the divergent test. Okay, so I need to write it down, the divergent test. Now what the divergent test do, so if the series, this is the series En, is convergent, then limit n approach infinity An equals to 0. Okay, if the series An is convergent, then the limit as n approaches 0, An is 0. If the limit, okay, let's go. If the limit n approach infinity An is not equals to 0, or this limit does not exist, then the series that An, I'm talking about the An series, is divergent. Okay, so a quick example will be something like this. Okay, so let's say I have this series summation n equals to 1 to infinity n squared minus 1. Okay, now how can I show whether the series converge or diverge? So apply the limit. So limit n approach infinity n squared minus 1. Obviously, by the divergent test, you get infinity. So apply n approach infinity to An. Okay, An. And if An equals to 0, it is convergent. But now An is not 0, right? Or this limit does not exist. So we call it diverges. Okay, so you directly you apply the divergent test, and so if the divergent test fail means the limit you can get equals to 0. Okay, so that's all for telescoping series. So let me just summarize. What is telescoping series? So telescoping series is a series that you arrange it such that the every term cancels out except the first and the last term. Okay, and if the first and the last term are not cancels out, that means you have a telescoping series and you can apply limit to the partial sum to determine whether it's converge or diverge. Okay, let's look at one more example here. Example number 2. So this example here given as this. Okay, determine if the following series converges or diverges. So if it converges, find its value. Okay. So the question is given for this series. N equals to 0. Oh, n equals to 0. That's interesting. 1 over n squared plus 3n plus 2. Okay, so this is the series given here. Now, by divergent test, let's look at by quick divergent test. Okay, by divergent test, so just take the limit for n approach infinity for the series here, an. So n squared plus 3n plus 2. Now what you get? Divide by the denominator highest power n squared over n squared, 3n over n squared plus 2 over n squared. So you see that this term is 1. This term will give you 2 over n, 3 over n, 2 over n squared, 3 over n, 1 over n squared. As n approaches infinity, 1 over infinity approaches 0. So this term approaches 0. Now, by the divergence test earlier on, it said that if the series an is convergent, then by the divergent test, it must give you 0, right? Okay, that means by quick divergent test, we know the series converges. Okay, the series converges. But the question asks you to find its value. Okay, therefore we need to simplify this and solve this. So what do you need to find here? You find the, because it says find its value, you need to find the partial sum for this term here. So Sn equals to summation I equals to 0 to infinity 1 over I squared plus 3i plus 2. Okay, again, this looked like a partial fraction, right? We need to simplify this by partial fraction. So I have 1 over I squared plus 3i plus 2. So I think I can factor it out. That will be I plus 2, I plus 1. Okay, so by partial fraction, so you can split it to a over I plus 2 and bi over I plus 1 and so on. That will give you 1 over I plus 1 minus 1 over I plus 2. So this is the partial summation. So remember, when I multiply it and expand, I should get back the same equation here. Okay, so this is the uh, partial fraction for this term. Okay, you need to work this out. Okay, now what we can do here, so I can say that Sn equals to summation I equals to 0 to infinity 1 over I plus 1 minus 1 over I plus 2. Now I'm writing the bracket so that it simplify you. So let's find when I equals to 1. So I have a 1 over 1 minus when I is 0, 0. So minus half. Now when I is 1, 1 over 2 minus 1 over 3. When I is 2, 1 over 3 plus 1 over 2. When I is 3, 1 over 4. Sorry, it's not plus, it's minus. Okay, that's what happened when you're writing it too fast. When I is, did I say 3? 3 plus 2, 5. Okay, you can see the pattern here, right? And then what is the term when I is n? So plus, whatever plus. So I think we should find n minus 1 first. So what is when I is n minus 1? So I have n minus 1 plus 1, 1 over n minus 1 over n minus 1 plus when I is 1, 1 over n plus 1 minus 1 over n plus 2. Now, look at it. I just want to write it down so that you don't get confused. This is not n, this is I equals to 0. This is I equals to 1. This is I equals to 2. This is I equals to 3. Now, this is I equals to n. So what happens if I don't find n minus 1? I will have this term that never been cancels out. So I need to find the term when I equals to n minus 1. Let's check. When I equals to n minus 1, I n minus 1. So it should be positive sign. Okay, why I know this is wrong? Because I need to cancel out with this term here. Okay, now this term and this term cancels out. And I know this term will cancel out with this term. Okay, and this term will cancel out with this term. This term will cancel out with this term. And this term will cancel out with the previous term here. And this term also cancels out with this term. So it should be 4 here. Sorry, that's why this term cancels out. Okay, so I have 1, 2, 2, 3, 3, 4, 4, 5, and so on. Okay, so please take sure this is 4, not 2 just now. I wrote it. So remember, this is a type of telescoping series. Telescoping series will give you the first term and the last term. Okay, so this is my Sn. So now I can apply the limit. So limit n approach infinity, Sn equals to limit n approach infinity 1 minus 1 over n plus 2. So when n approach infinity, 1 over infinity approach 0. So the value is 1 and it converges. The sum is converges to 1. Okay, so this is the example of telescoping series that we continue. Now, that is also another type of series. Okay, there's another type of series that I would like to explain or discuss, which is called the, what do you call it? Harmonic series. Yes, okay, harmonic series. So let's look at harmonic series now. So harmonic, how does harmonic series look like? Okay, so this is harmonic series. N equals to 1 to infinity 1 over n. And this series is divergent. Okay, the harmonic series is divergent. Always. Okay, so we can show that, we can prove that. How do we prove that? So I have this example here. So the first example, summation n equals to 1 to infinity 5 over n. So let's say I factor out the common term here. So summation n equals to 1 to infinity 1 over n. Now, obviously, you can see that by the divergent test, you will get 1 over infinity, which is 0, right? So it must converge. But this is a special case where you cannot apply the divergent test. So we must look at another test that is called the integral test. Okay. So let's say we want to apply this to the partial sum. Okay, before you apply the integral test, let's look at you want to apply the partial sum, right? So what do you get? You get Sn equals to summation. Forget about the 5 there. I equals to 1 to n 1 over I. Okay. Now, what happened here? If I draw a table now, which is n and Sn. Okay. Let's say when n is what is my n? N is 5. Okay, so n is 5. Let's start with 1. Okay, when n is 1, so I have 1 here. And now when n is 2, see when n is 2, I have 1 plus 2, right? So 1 over 1 plus half here. So I just gotta write it down so that I remember what am I doing. Right? Until 2. So when n is 3, I have 1 plus half plus 1/3. Okay, now so on. Now let's say this is 1. This is 1.5. Okay, what is 1.5 plus 1/3? Okay, I gotta find my calculator and do it quickly. So 1.5 plus 1/3 will give me 1.8333 and so on. Now when n is 5, you can see that my partial sum will be 1 plus half plus 1/3 plus 1/4 plus 1/5. That would give me 2.2833. Okay, you can see that one thing you can observe that the partial sum increasing, right? It increasing. You can see that from this table, you can show that as n increases, the series also increases. I mean, not rapidly, but the number will always get bigger and bigger. Okay, you can try for n equals to 10, 100, and so on. So that's why we will say the series diverges. Now we can also do that by using integral test. Okay, so to do the integral test, what is integral test? Yeah, what is integral test? Let me just uh, write it down. The definition of integral test. So suppose f is a continuous positive. Look at the term here, continuous positive decreasing function on 1 to infinity interval, and let an is f of n. The series summation n equals to 1 to infinity an is convergent if and only if the improper integral 1 to infinity fx dx is convergent. So, to find this series convergent or divergent, you need to apply the improper integral. And to show that whether you get a finite value. If you get a finite value, then you will say that the series converges. Okay, we'll look at it in a few while. Okay, don't forget the 5 years. So if you add 5 here, of course the series will also diverges. Okay, let's look at another example. Okay, therefore what I can say that, so we want to apply integral test to this series. 5 over n, that was our given series here, right? So this is what we want to find out by the integral test. So by the integral test, we must make sure that f is continuous. So I can say that let fx equals to 5 over x. Okay, just check. Is it continuous? Yes, it's continuous. It's positive and decreasing function. Correct. Okay, so I can apply integral test. Now, by the integral test, say that limit, sorry. So integrate 1 over infinity 5 over x dx is equals to limit t approach infinity 1 over 3 5 over x dx. Now 5 is a constant, I can take it out. Limit t approach infinity. Now integrate 1 over x, that will give you ln x from 1 to t. Okay, so 5 limit t approach infinity ln t minus ln 1. Okay, so please check whether I have written this correctly, right? When x is t, we will get ln t, and then minus when x is 1. So ln 1 is 0, which is good. That will leaves with ln t. So what is t approach infinity? We have 5 ln infinity, which is infinity. Okay, so we know that by the integral test, the harmonic series diverges. So this is true for every harmonic series. So this is why that all the harmonic series. So harmonic series must be in this form. N equals to 1 to infinity 1 over n, or n equals to 1 to infinity if I have 6 over n. It's 1 over n pretty much. They all diverges by the integral test. Okay, but if you do a divergent test, it will converge, right? But this is a special case where you use a integral test. Okay, now I would like to explain more about this integral test. I want to give you one more example for this integral test. Before we will look at, or maybe I'll look at in my next video. Okay, I'll give you some example about integral test in my next video. Okay, that's all. Bye.